let's move on to relate between the linear speed and also the angular velocity. So we are going to involve time in this discussion right now. Previously, when we relate between s and theta, there's no time involved here. Okay, but now let's involve time in it. So let's say this rotation here, this rigid body here is going to undergo this rotation that will take up the time of 2 seconds. So for the rigid body to rotate from being horizontal to be at an angle here, this whole rotation here takes up 2 seconds of your time. Okay, so now we see that we are again interested with this point over here, and this point is having a distance of 4 meters from the axis of rotation. Okay, so this here represents r, but right now r is the distance from the axis of rotation. Okay, again, our point on the rigid body here, this point that we're interested in, has already covered a distance over here. Okay, so now we can study two different quantities based on what we have here. First is we can study how fast is a point on the body moving in circular path while the body is rotating. Yes, the body is rotating, but now I'm interested in this particular black sticker over here. How fast does it travel this distance over here? Okay, so to determine that, that will be the first quantity that we can determine. A second quantity that we can determine is how fast is the body is rotating. So this body here has changed its orientation from being fully horizontal to be at an angle. So how fast does this rotation happens? That's the second thing that you can calculate. So the first thing that we're referring here is the linear speed. Technically, it means that this black sticker here, how fast is it moving? And because the motion trace out is a circular path, so we call it linear. Because we're not going to talk about angle, we are going to talk about distance. So for this second value over here, because it's related to rotating talks about change of angle. So in this case, it will be an angular quantity. So this is angular velocity, omega. Okay, linear means by they are talking about the distance. Angular here means by they are talking about the angle. Okay, so if you want to determine the average linear speed we learn from kinematics of linear motion, it's distance divided by time. So it's still the same idea over here. You are going to take the linear distance, which is this red arrow here, and you divide by the time taken to travel this distance of the red arrow over here. We know that s over here, it's the linear distance, and we learned from a previous video that s is equals to r theta. So you can change s to become r theta. You know that the distance, which is r, is 4 meters, and you know the angle swept by this point over here is 45 degrees. Again, to use this equation, theta must change to be radian, and we know that this is pi over 4 radian. So you can substitute 4 to represent r, pi over 4 to represent theta. The time taken for this motion over here from this point to this point takes up 2 seconds. So from here, you can do a calculation. You see that the average linear speed that we have here, it's pi over 2 meters per second. So it means by every second, let's say for the first second, you travel a distance of pi over 2 meters. So here to here will cost pi over 2 meters. Then once you reach the second number 2, then you travel another pi over 2 meters. That's why the total distance that you have traveled is pi over 2 plus pi over 2 within these 2 seconds. That's why that is pi. Okay, so you can see that s here, which is r theta, if you multiply, you'll get s is equals to pi meter. Okay, every second you move a distance of pi over 2 meters. From here to here, pi over 2. From here to here, pi over 2. Okay, how about angular velocity? Angular velocity is still similar to what we learned in last chapter. So for average angular velocity, it will be the angular displacement divided by the time taken. How much angle have you swept through? How much time does it take for you to sweep through the angle? So the angle again is 45 degrees. So the 45 degree change into radian, that will be pi over 4. The time taken for you is 2 seconds. So if you calculate it, it will be pi over 8 radian per second. So it means by every second, you sweep through an angle of pi over 8 radian. So the first second, you sweep through this angle from here to here. From here to here, that's 22.5 degrees. And if you calculate into radian, it's pi over 8. Second number 2, you move another pi over 8 radian to reach this 45 degree over here. Okay, this tells you how much angle you swept through for every second. Okay, so now if you understand linear speed, you understand angular velocity, you can see that the average linear speed is r theta over time. The average angular velocity is theta over time. The difference between these two equations is that one have r, the other does not have r. So if you take the angular velocity, if you multiply the whole equation by r, then it will change to become linear speed. That's why we know that if we take omega multiplied by r, you get the linear speed, which is v. That's why we get this relation, v is equals to r omega. Okay, but this is an average equation. What we can do is we can limit the time, the duration of this thing from 2 seconds that we see just now. Let's limit it to a very small, infinitesimally small time. We limit the time here to be near 0. When that happens, we are focusing for a particular moment. So now this equation has changed from an average equation to be an instantaneous equation. Okay, previously this equation is focusing on the rotation for a particular period of time. From here to here, it takes out a certain amount of time. But now, if you change it into this equation is focusing on at any particular moment, what is the linear speed? At any particular moment, what is the angular velocity? For any particular moment, let's say this moment, let's say when it's swiping through this moment, what is the linear speed? What is the angular velocity? They are focusing on a particular moment. Okay, these equations here can also be converted into instantaneous form. Just change the delta to become d. Okay, so you can get this equation, which is the instantaneous form of the linear speed. So this is linear instantaneous linear speed. This is instantaneous angular velocity. Just change all the change to become infinitesimally small change, d. Okay, so d theta over dt is instantaneous angular velocity. D dr or ds over dt is instantaneous linear speed. Okay, so this is how we relate between v and omega. V is equals to r omega, and we can see that all these equations here has an average form for a period of time and also an instantaneous form for a particular moment. Okay. Another thing that is important when we are talking about average and instantaneous value is that if our object here is rotating, if the object, the rigid body, is rotating with a constant rotation speed, means by it does not speed up, the rotation does not speed up, the rotation does not slow down, it rotates at a constant speed, then we will see that the average linear speed will be equal to the instantaneous linear speed. Whereas the average angular velocity will be the same as the instantaneous angular velocity. Okay, so this is similar to what we learned in chapter 2. In chapter 2, we learned that if an object is moving at constant velocity, the average velocity will be the same as the instantaneous velocity. If an object is moving at constant acceleration, the average acceleration will be the same as instantaneous acceleration. Constant acceleration, then the average should be equal to instantaneous. Constant velocity, then the average should be equal to instantaneous. So it's still the same idea. If the rotation is having a constant speed, then the average linear speed will be the same as the instantaneous linear speed. Average angular velocity will be the same as instantaneous angular velocity.